Good day and welcome. It is my pleasure to present this webinar. We appreciate you taking time out of your schedules today to meet with us for the next 30 to 40 minutes discussing emissivity and the potential impacts this property may have when making thermal measurements with an infrared camera. The agenda for today's webinar is as follows. First, I will address what it means to measure temperature with temperature measurement technologies available today. Then, I will review some general infrared theory. I will then review the definition of emissivity, and we will discuss what reflected radiation is and how it might impact or influence temperature measurement with an infrared camera. Following this, I will demonstrate some methods used to work with emissivity and produce accurate quantitative temperature measurement results. And in closing, I will summarize what we learned today. Now, I will point out that the subject of emissivity is an extensive one. And typically, for individuals involved in thermal imaging and measurement applications, the training on emissivity is covered over a couple days in training courses that are approved by the American Society of Non-Destructive Testing, or ASNT. The content presented today is but a brief glimpse into emissivity theory and how to compensate for reflected radiation interferences. If you're interested in learning more about these ASNT training courses, please contact your FLIR representative. Okay, let's get started. First of all, do you realize there is no direct method to measure the absolute temperature? All temperature measuring devices report or they calculate a temperature value by measuring an effect of temperature. For example, a thermistor measures changes in resistance associated with changes in temperature. A thermometer measures changes in volume associated with changes in temperature. A thermocouple measures changes in voltage associated with changes in temperature. An IR thermometer or spot pyrometer also measures changes in voltage associated with changes in temperature. And an infrared camera, more specifically the infrared camera I will refer to in today's webinar, measures changes in resistance associated with changes in temperature. Now, all of these instruments that I've listed here, they report a temperature value based upon the measurement of some other parameter. Now, for today's webinar, we will focus primarily on infrared cameras. As such, let's now discuss how infrared cameras see infrared radiation and report temperature values. Let's first look at the operation of a FLIR T420 infrared camera. Now this camera, the T420, has an uncooled microbolometer focal plane array infrared detector. A microbolometer is a thermal-based sensor, meaning it produces a resistance change when heated. Now, the focal plane array in our camera, it contains 320 by 240, or over 76,000 individual detector elements. Each one of these elements being a single bolometer. Now, with the lens of our camera, we can focus infrared radiation onto these detector elements. And as the radiation strikes our elements, they heat up, and their respective resistance changes. Now, using a readout integrated circuit in our camera, we can measure the resistance change for each of the several thousand elements and convert the readings into a digital count. Most cameras digitize at 14 bits or 2 to the 14th power. This digitized data from each element is then calibrated to a temperature, assigned a color or grayscale value, and presented as an image. Now, because our image is made up of individual detector element measurements, we can use analysis tools to highlight specific elements and display their respective values. For example, I can use an area analysis tool to display the maximum, minimum, or average temperature within an area. I could also use spot tools to display the specific temperature values from any element within my image. Now, in a way, my T420 camera is like having several thousand, over 76,000 IR thermometers or spot pyrometers or thermocouples in the palm of my hand to make temperature measurements. Now, because our discussion today focuses primarily on infrared radiation and infrared cameras, let's review a little infrared theory. And we're going to start at the molecular level. Now, as a medium or material, and that medium or material could be a fluid, a gas, or a solid, as that medium heats above absolute zero, and absolute zero being minus 273 degrees C or minus 460 degrees F, as that medium heats above absolute zero, the molecules within the medium start to move. And as these molecules move around, they collide with each other, creating a release of energy in the form of photons. And as the temperature of our medium increases, so do the molecular collisions. Thus, an increase in temperature produces an increase in collisions, resulting in an increase in the release of photons. This form of heat transfer caused by the release of photons is known as thermal radiation or infrared radiation. Now, this thermal or infrared radiation is what is sensed or seen by an infrared camera. The chart shown here is a representation of the electromagnetic spectrum. From the chart, we see how infrared radiation relates to other forms of electromagnetic radiation. Some key takeaway points are infrared radiation wavelengths are larger than visible wavelengths. These are the wavelengths that our eyes are tuned to see. Yet infrared radiation wavelengths are shorter than radio wavelengths. And like visible light, infrared radiation travels through space at the speed of light. Like visible light, it can be focused, it can be reflected, it can also be refracted. Now, an important property in the field of infrared theory is emissivity. And in basic terms, emissivity describes how well a target or a material emits infrared radiation. A perfect emitter is known as a blackbody and has an emissivity value of 1. Or in other words, the radiation coming from that material is 100% emitted. Now, in reality, there are no perfect blackbodies, so most materials have an emissivity value less than 1. Let's take a closer look at this property of emissivity in the next slide. And let's look in more detail as to how emissivity might affect the measurements we take with an infrared camera. Now, in this example that I have here, we have a target that we want to measure and report a temperature for. Now, this target happens to be a perfect blackbody. It has an emissivity of 1, or in other words, the infrared radiation from the target is 100% emitted from the target surface. Now, this is a good time to point out the difference between actual temperature and apparent temperature. The actual temperature is the actual or the true temperature of the target of interest. The apparent temperature is the temperature value reported by our infrared camera. And I say reported temperature value and not measured because, as you remember from our previous discussion, our infrared camera does not measure temperature. Our infrared camera measures the effective temperature, perform some mathematical calculations related to a calibration process, and then reports a temperature value. Now, our goal when using an infrared camera is to try and make the reported apparent temperature be as close to or equal to the actual temperature of the target. Okay, let's explore this in more detail. As previously discussed, in reality, the targets we are likely to measure, they are not perfect radiators or perfect black bodies. Our targets will have emissivity values less than 1. As such, the total radiation reaching our infrared camera could be a combination of emitted, transmitted, and or reflected radiation. Now let's define what transmitted and reflected radiation is. Transmitted radiation is the radiation which passes through the target of interest. It is similar to seeing light pass through a piece of glass. Reflected radiation is radiation from a source in front of the target that reflects off the target's surface. It's like seeing your reflected image in the surface or from the surface of a mirror. Now, the temperature associated with this reflected radiation, it's known as the reflected apparent temperature. It is sometimes also referred to as T reflected or T background. Now, the infrared camera sees the total radiation from the target of interest. And the infrared camera, it cannot differentiate between the various sources of radiation on its own. It is the camera user who must tell the instrument what makes up the total radiation. So the instrument can calculate and report an apparent temperature close to the actual temperature. Now let's discuss further the potential impact of reflected radiation and how it might influence our IR camera measurement. And I'm going to do this through a couple examples. Now, in this example, let's assume that the target of interest is opaque, meaning there is no radiation transmission through the target. And let's assume that the target has an emissivity value of 0.75. Or in other words, the total radiation from the target will be 75% emission and 25% reflection. Let's also assume that we have made no emissivity adjustment to the infrared camera. As such, the camera will make no compensation for the reflected radiation. How might the reflected radiation impact the camera measurement? Well, it depends. It depends upon the temperature of the reflected source. It depends upon the value of the reflected apparent temperature and the temperature difference from the actual temperature of the target. Okay, let's look at a couple examples and see how this works. Let's say that we have our same target, which has an emissivity of 0.75, and let's say that the temperature of our target, the actual temperature, is 40 degrees C. Let's say that our source of reflection is a very large cup of ice water, which has a temperature of 0 degrees C. Now, in these examples, let's assume that we have done nothing to the IR camera to compensate for emissivity. Will the infrared camera in this example report an apparent temperature that is higher or lower than the actual target temperature? Well, in this example, the camera will report an apparent temperature lower than the actual temperature. You can think of it like this. Think of it like pouring 25 parts of cold water into 75 parts of warm water at 40 degrees C. Similar to the cold water diluting the warm water, reducing its temperature, the colder reflection radiation will dilute the warm radiation emitted from the target surface. As such, our camera, with no adjustment, will report an apparent temperature less than the actual temperature. Let's look at another example. Again, let's say that our target of interest has an emissivity of 0.75 and the temperature of our target is 40 degrees C. In this example, though, let's say that the source of our reflection is a very large fire that has a temperature value of 500 degrees C. Once again, let's do nothing to our IR camera to compensate for emissivity. Will the camera, in this example, report an apparent temperature higher or lower than the actual target temperature? Well, if you said the IR camera will report an apparent temperature higher than the actual temperature, you are correct. The 500 degree reflected radiation will add to and increase the 40 degree radiation emitted from the target. Now, from these exercises, we learn that not only is it important to know the emissivity of the target, but it is just as important to know the temperature of the reflection source, or it's just as important to know the reflected apparent temperature. Later in the webinar, I will demonstrate how to determine the reflected apparent temperature using an infrared camera. But first, let's discuss how you determine the emissivity of your target. One way is to reference an emissivity table. The emissivity for most materials can be found in tables like this. Emissivity tables can be readily found online. They can be found in heat transfer textbooks. And most infrared camera manuals include an emissivity table. And we can learn a lot from emissivity tables like this. For example, from the table, we see that different materials have different emissivity values. For example, we see both brick and human skin are better emitters than aluminum. Brick and human skin having emissivity values greater than 0.9, and aluminum, in this case polished aluminum, having an emissivity value less than 0.1. Second, we see that surface roughness impacts emissivity. I've highlighted here roughened aluminum and polished aluminum. We see the roughened aluminum has a higher emissivity value or is less reflective than polished aluminum, which has a very low emissivity value. Third, we see that emissivity can vary by wavelength. Looking again at our roughened aluminum, we see that there are different emissivity values for the mid-wave IR spectrum at 3 micron and the long-wave IR spectrum at 10 microns. Finally, from the table, we see that the emissivity values listed here are at specific temperatures, indicating emissivity can vary for a given material with changes in temperature. In summary, we learned from a study of this table that emissivity can vary with material, with surface roughness, with wavelength, and temperature. Additionally, emissivity can vary with camera viewing angle, and it can also vary with surface geometry. So what happens, or what can you do if you cannot find your material listed in an emissivity table? Or what if you require to know the specific emissivity of your target for your specific conditions? Well, there are methods available for determining emissivity, and we will uncover some of those methods in the demonstration that follows. Now, my demonstration for the webinar today is very simple. What I am going to do is I am going to image and measure the pouring of hot water into a stainless steel cup. And I will use a thermocouple placed inside the water in the cup as a comparison reference for my infrared camera. Now, you may recall from a previous webinar titled Thermocouple versus IR Camera Measurement that we learned that type K bead wire thermocouples do report reliable temperature measurements for fluids and gases. Now, in my demonstration, I will use the following equipment listed here. I will use a FLIR T420 benchtop test kit. I will use an X-Tech Type K thermocouple. I will use a stainless steel cup. I will use Scotch 3M electrical tape, and I will also use some foot powder spray. I'll explain shortly why I'm using the 3M tape and the foot powder spray. Let's first, though, take a look at our stainless steel cup with our infrared camera at steady state with no hot fluid in it. The IR image presented here with its corresponding color palette and temperature scale would lead us to believe that there is a temperature variation across the stainless steel cup. Additionally, I have drawn a line region of interest, or line 1, across my stainless steel cup, and I've displayed the corresponding line profile. This line profile also indicates a variation in temperature across the stainless steel cup of almost 10 degrees C. Now, this apparent temperature variation shown here is a lie. In reality, there is no thermal variation across the surface of the stainless steel cup. The apparent variations shown here are a direct result of low emissivity and reflected radiation. As a general rule, targets with low emissivity, below 0.7, are difficult to measure. And targets with very low emissivities, below 0.2, well, they are very difficult and sometimes impossible to measure. The good news is there are ways to compensate for low emissivity on targets. First, anything that can be done to reduce the surface reflectivity, like applying a surface coating or roughening the surface, this will improve the measurement accuracy. Second, there are camera and software tools that can be used to mathematically correct for reflected radiation interferences. Third, adjusting the camera to target angle or controlling the image environment. The imaging environment can change or can reduce reflected radiation interferences. Finally, changing the geometry of the target can create locations with improved emissions, and an additional software functionality, subtraction, can be used to adjust and correct for emissivity. Now let's explore these correction methods in more detail. First of all, let's discuss coatings. There are primarily two categories of coatings, temporary and permanent. And listed here in this slide are various temporary and permanent coatings with high emissivity. High emissivity value of 0.95. Remember, this means 95% of the radiation from these coatings will be emitted, while only 5% will be reflected. Let's return to my stainless steel cup demo. To improve my imaging and measurement results, I will apply two temporary coatings to my stainless steel cup. I will apply 3M electrical tape and a strip of foot powder spray. Now, from the emissivity tables, I know that my 3M electrical tape has a high emissivity value of 0.95. I'm not certain, though, of the emissivity value of my foot powder spray. However, I do know from a visible perspective that the foot powder is less reflective than stainless steel. And generally, it should be less reflective in the IR spectrum. Now, there are methods available for determining the unknown emissivity values, as I discussed earlier, and I will show you how this is done. But first, as you remember, just as important as knowing the emissivity of our targets for accurate measurement is the need to know the reflected apparent temperature. And I'm going to show you how to determine the reflected apparent temperature in this slide here. First, we need to place a sheet of crumpled aluminum foil in front of the target of interest. And you may have caught this from the emissivity table shown earlier that aluminum foil has a very low emissivity value of 0.04. It is highly reflective. The second thing I'm going to do is on my camera, or I could do this in software, I'm going to set the emissivity value to 1 and the distance to 0. Now, with these camera settings, I'm telling the camera that all radiation measured is emitted and that there is no attenuation due to the atmosphere. Now, the third thing I'm going to do is I'm going to place an area region of interest on the foil target in my infrared image. And I'm going to measure the average temperature from that region of interest. This average temperature is the reflected apparent temperature. Now, the final thing I'm going to do is I'm going to enter the reflected apparent temperature into the camera and or the software. And I've shown here in this slide an image of the object parameter menu from the analysis software that is included with the T420 Benchtop test kit. This menu contains the input locations for the overall image emissivity, the camera distance to target, and the reflected temperature. Now, using the method previously described in the previous slide, I determine the apparent reflected temperature for my demonstration to be 23.1 degrees C. Now, I will input this value into the Object Parameters menu in the analysis software. Let's now look at our demonstration of pouring hot water into our stainless steel cup with no emissivity correction applied. And what I'm going to do is I will record a thermal movie file of pouring the hot water into the stainless steel cup. Once I've recorded that movie file, I can go back and perform analysis. The analysis I'm going to perform is to apply area tools or area regions of interest to the foot powder, the stainless steel, the 3M tape, and the aluminum foil surfaces. The plot in this slide shown here is generated from the analysis software, and it represents a temperature versus time plot from my 4 regions of interest. The brown line shows the apparent reflected temperature measurement, and this appears to be fairly constant. The green, the blue, the red lines represent the stainless steel, the 3M tape, and the foot powder temperature measurements respectively. Now, from this chart, we see the 3M tape and the foot powder coatings produce fairly accurate results without any emissivity correction when compared to the internal thermal couple temp of 51.9 degrees C. The measurement from the stainless steel cup, however, varies dramatically from the internal thermocouple measurement, with a difference of more than 25 degrees C. Now, let's see how we can improve these measurements through emissivity correction. And there are essentially 2 methods for doing this. The first method is simple. It does require that I know the true temperature of our target, which in this case is the internal thermocouple measurement of 51.9 degrees C. What I do is I simply adjust the emissivity value for the region of interest or the analysis tool until the reported temperature from that region of interest equals the actual known temperature. Now, it may take a few iterations, but eventually the measurements will match and I will have determined the emissivity of my region of interest. Or in this example, the emissivity value of the foot powder coating and the stainless steel. The second method for determining emissivity is the easiest. It involves using what's called an emissivity calculator, which I've shown here. The analysis software that I used in my demonstration that comes with the FLIR T420 and the Thermal Benchtop test kit has a built-in emissivity calculator. And how it works is you simply apply a region of interest or an analysis tool to the target. You enter the actual temperature, or in this case, the internal thermocouple measurement, and you press calculate. The software will calculate the emissivity value for that region of interest and then assign that new emissivity value to that region of interest. Some notes regarding the usage of an emissivity calculator. First of all, I must know the actual temperature of the region of interest, which I did. You must also know the apparent reflected temperature, which I did, I had measured. And a third note is that this is a mathematical correction, and it will adjust and change the mathematical reporting or output from the region of interest, but it doesn't change the appearance of the image. Okay, so now let's go back and look at our time versus temperature plot with corrected emissivity values for our coatings and also the bare stainless steel surface. The results from the emissivity calculated are presented here in this table. And as expected, the foot powder has very good emission properties. It has an emissivity value of 0.925. Or in other words, the powder is 92.5% emissive and only 7.5% reflective. The plot shows the corrected calculated temperature for the powder tracks almost exactly with the 3M tape. Now, speaking of the 3M tape, I thought I would go ahead and use the emissivity calculator to double check my table results, my emissivity table results. And the calculated result matches the table perfectly at 0.95. Now, finally, let's look at our stainless steel. The emissivity calculator generated an emissivity value of 0.099, or in other words, 9.9% of the radiation coming from the stainless surface is emitted, while 90.1% of the radiation is reflected. The stainless steel cup is a terrible emitter, but even so, using the emissivity correction, the reported temperature tracks closely with the tape and the powder coating measurements. Remember, the stainless steel value is plotted in green. Let's talk about some other methods that are available for working around or correcting for reflected radiation. In this example here, I am imaging a printed circuit board, or PCB, in a non-energized steady state. What that means is that there is uniform temperature across my printed circuit board. Now, the bottom left thermal image was taken with my printed circuit board exposed to the environment of the lab. And as you can see from this thermal image, there is considerable color variation in the image. Remember, color variations represent different temperatures. So this image shows temperature variation across my printed circuit board. This variation is the result of reflected radiation because my printed circuit board is at steady state. The bottom right thermal image was taken of the printed circuit board with the infrared camera to target angle varied just slightly. Now, this infrared image shows a substantial reduction in color variation, or apparent temperature variation. As a general rule, as long as I stay within 40 to 45 degrees normal to my target of interest, I should get good temperature measurement results. And I can vary or reduce the reflected radiation by simply adjusting the camera to target angle. Let's look at another way to control or to reduce reflected radiation interferences. In this example, I'm going to control the environment of the reflected radiation. Now, in this example, I am imaging the same target, the printed circuit board, at a non-energized steady state condition. Once again, that means uniform temperature across my printed circuit board. The top right thermal image was taken with the PCB exposed to the environment of the lab. And just like before, there is substantial color variation or apparent temperature variation across the board. Like before, this variation is a result of reflected radiation. The bottom right thermal image was taken of the printed circuit board in a controlled environment, meaning I reduced or I eliminated the reflected radiation sources. This image, the bottom right image, is a truer representation of reality. There is no color variation, which means there is no apparent temperature variation. So how did I do that? How did I remove the reflected radiation sources by controlling the environment? Well, I did it quite simply by using a cardboard box placed over my printed circuit board with a hole cut in the box to view through. It was that simple, but the results are dramatic. I essentially eliminated those reflected radiation sources by shielding my printed circuit board from them, utilizing the cardboard box. At this point, I will discuss another software method that is available for working with emissivity, and this method is called image subtraction. Image subtraction does what the name implies. It is a subtraction of one image from another image, or it is the subtraction of one image from a sequence of images. This functionality is also available in the software that is packaged with the T420 Thermal Benchtop Test Kit. The process of image subtraction is simple. The user selects the result image or movie. This is the desired image or movie to be analyzed, and subtracts from that a designated baseline image. Baseline images are typically those images that are at steady state that are non-energized. Now, unlike mathematical emissivity correction, which does not change the appearance of the thermal image or movie, image subtraction removes the visible interferences of reflected radiation from the image or movie. So it does make a difference in the viewed image. A final point regarding image subtraction. If the objective is to conduct quantitative analysis of the subtracted imagery, the correct target emissivity values must still be applied. If we were to review the math behind image subtraction, it would show emissivity does not cancel out. Okay, let me show you an example of image subtraction and how it works. This is a baseline infrared image of a non-energized steady-state heater board. Each of the small circular areas in this image represent an individual rough aluminum heating element. These elements are roughly the size of a quarter. Now, some of these elements are painted black, some are painted white, some are painted gray, and some have no coating applied at all. As mentioned, this entire heater board is at steady state, meaning the board and each heating element are at the same temperature. However, due to varying emissivity values of the coated and non-coated elements, the elements appear to have varying temperatures. Some appear dark blue, corresponding to a cooler temperature, while some appear a lighter shade of violet, corresponding to a warmer temperature. We know this to be false. The color variation or temperature variation is the result of reflected radiation. The image shown here is our results image. It's the image that we're interested in analyzing. It is a thermal snapshot of the heater board with one of the heating elements energized. Would you like to guess which element has been energized? Because of the reflected radiation interference, it is almost impossible to say which element was energized. However, if we subtract from this results image the baseline image, it becomes very easy to determine which element was heated. The white colorization in this image represents a 1 degree Fahrenheit temperature difference. Utilizing subtraction, I am able to remove the reflected radiation interference and clearly see subtle temperature differences on my reflected target. These images shown here in these slides are a great example of how image subtraction can be used to detect very subtle temperature differences on reflective targets. Now, some final points regarding image subtraction. In order for image subtraction to work properly, you must have exact target alignment from the baseline to the results image or to the movie file. And again, as previously discussed, accurate quantitative measurement requires the entry of true emissivity values. During the webinar today, I've referenced a couple times this thermal benchtop test kit, and I thought I would explain in more detail what that is. The thermal benchtop test kit is a turnkey out-of-box analysis package. And there are actually two variations of the thermal benchtop test kit that is available. The first one is the T420, which includes the T420 thermal camera. It includes a 25-45 degree lens, and it also includes the advanced real-time recording and analysis software that I've demonstrated in the webinar here today. The other kit that is available is the E40 benchtop test kit, and it's very similar to the T420 kit. It includes the camera, the two lenses, and it includes a real-time recording and analysis software. In closing, let's review what we learned from today's webinar. First, we learned that emissivity is an important parameter to understand and correct for when using an IR camera for thermal imaging and temperature measurement. We also learned that knowing the apparent reflected temperature of our reflection sources is just as critical as knowing the emissivity of the targets of interest. We learned that emissivity varies with material, surface roughness, wavelength, temperature, viewing angle, and surface geometry. We learned that coatings, surface roughness, camera and software adjustments, viewing angles, environment, geometry, and subtraction are methods available for working with emissivity and reflection interferences. We learned that IR cameras are great tools for non-contact temperature measurement, and that the thermal image combined with the several thousand measurement spots take the guesswork out of thermal analysis. And finally, we also learned that the subject of emissivity and reflectivity is typically covered more extensively in ASNT accredited training courses. Again, I want to thank everyone who participated in today's webinar for taking time out of your schedules to meet with us to discuss the property of emissivity today. If you have specific questions regarding your application for infrared thermography, feel free to reach out to me as well. Again, thank you for your time, and we look forward to meeting with you again in future webinars.